We have 9 hours ahead of you. You want to take a stretch right now, you should. So let me say a few words about what this course is going to cover. So as Ramesh already alluded to, that wireless communication has been around and since Marconi times, over 100 years. But what happened in the past 10 years have been really quite exciting. Exciting in the sense that both in terms of the new ways of thinking about how to communicate over the wireless channel, as well as developments in industry. So basically, because of this recent development, we decided to go ahead and commit a very, very foolish act, which is to write a book, to write a textbook. And that took us fully 2 years of our time. And the key idea is to really try to give a unified view on the traditional way of communicating over wireless channel and a modern way of communicating over the wireless channel. So the course here is really stemmed from that book. It's really how to study in a unified way the fundamentals as well as the new developments. In parallel to this theoretical development, as I said, actual systems are being deployed. Many systems have been deployed in the past 10 years. A lot of them has embodied the concepts that I'm going to talk about as well. So I'm going to use as examples various systems, as you see here, to illustrate the conceptual development. So one thing I want to emphasize about wireless communication in particular, but I think communication in general, is that there's sort of interplay between many different layers of the concept. And that's what I'm going to emphasize a lot in the book. So at the bottom layer, we talk about channel modeling. So the wireless channel is the sort of a central feature, and is very, very different from most types of other channels. So we're going to focus a little bit on that. And then we're going to talk about communication techniques and capacity limits over these wireless channels. And above that, we'll talk about how these techniques can be implemented as part of a system. So I think that's sort of one point that we stress a lot in the book and also in this short course, which is the importance of thinking about implementation of techniques in the context of the whole system, and not just as isolated point-to-point techniques. And I think that's really one way of how to turn these conceptual ideas into practice. So I want to emphasize on these 3 layers, and I'll be going back and forth between the different layers as I progress through the course. Okay, so let me say a few words about the course outline. First, I'll talk about the wireless channel, as I said. Then I will introduce one of the most important concepts in wireless communication, which is diversity. Okay? Diversity is introduced here as a point-to-point idea. So section 3 is more focused on point-to-point wireless communication. Then I will talk about how to think about wireless systems. And when you think about systems, you think about many users or many mobiles, infrastructure, base stations, etc. The important concepts there is multiple access and interference management. So the primary examples I will use from that is cellular systems. Okay, so this is the 3rd topic, which is moving up to the system level. Then I will talk about, I'll revisit some of these concepts more from a fundamental point of view, from a capacity point of view. So as Ramesh already said, a lot of the recent developments really come from the introduction of ideas from information theory into the wireless communication problem. And so to sort of set the stage for introducing the modern developments, I will talk a little bit about the capacitive wireless channel, and that will be probably the end of the first day. And on the second day, tomorrow, if any of you actually is coming back, on Saturday morning, this is a bit of a, but timing's tight, I guess. So tomorrow, I will talk about 2 modern developments which are built on top of what we learned in the day 1. The 2 ideas, one is I want to talk about this idea of opportunistic communication. That's number 1. And number 2, I'll talk about MIMO. I'll introduce the basic ideas of MIMO, how to think about MIMO, how to think about when MIMO will give significant performance gain. Okay, so that's the course. Now this whiteboard is in a location which is not the natural one. So a test. How many people can actually see this? All right, the bottom row is, the back row is the most important, okay? All right, so presumably this is for white rubbing out the whiteboard. Good, very good. All right. Okay, so, all right, so let's start. I do assume some background though. It's a bit hard to talk about wireless communication without any background. It's like there's not wireless communication for poets or something like that. So I do assume some basic knowledge in signals and systems, linear algebra probability, and basic digital communication. So how many people here have taken a course in digital communication? Okay, all right. A good number, so that's good. All right, all right. Okay, so let's talk about the wireless channel. The most striking feature about the wireless channel is the variation, okay? The channel strength typically varies over time. And if you look at the wireless channel, typically you will find variation of the channel strength at sort of two different spatial scales as you move, as the receiver moves, okay? On a large scale and on a small scale. So let me say a few words about the large scale fading. In large scale fading, typically as you move, as you change distances from the transmitter, the propagation, the signal strength get reduced, like inversely, like 1 over r squared in free space. Okay, so this is one example of why channel strength changes with distance. Typically, the attenuation is typically faster than 1 over r squared because of various obstruction, shuttling effect, ground reflection, and so forth. The model for this attenuation is rather complicated. Okay? However, this is not going to be the main focus when I talk about the wireless channel modeling. Okay? The reason is because the time constants associated with this variation, so this is essentially the variation when you move, say, from close to the base station to further away from the base station, or you go behind a mountain, go behind a mountain, you have shuttling and so forth. So this is happening at time scales of the order of seconds or minutes as the mobile moves. And we are more focused on communication system design. So when we're talking about communication system design, we are talking about how to send bits from point A to point B. And those bits are typically have to be sent in a much shorter time scale than minutes. Okay, maybe a fraction of a second, or longest, maybe 1 or 2 seconds. You have to deliver those information there. So therefore, we're focusing more on what happens over a shorter time scale. And so this is not really our focus. Of course, large-scale modeling is very important. You want to figure out how to how to roll out a wireless network, how to deploy enough base station to have coverage, etc. Then you have to worry about this large-scale effect. But this is not really the focus of this particular course. So then we move quickly to small-scale fading. Okay, so in small-scale fading, typically the main effect here is due to multipath. So let me explain a few words about the multipath. So wireless communication typically happens at very high carrier frequency, 900 megahertz, 1900 megahertz, cellular, 2.4 gigahertz, sorry, 1.9 gigahertz, not megahertz, so 1.9 gigahertz, 2.4 gigahertz for 802.11b, 5.3 gigahertz for 802.11a, etc. So very high carrier frequency. So what you're sending out are actually waves. And because in a wireless environment, you typically have this situation where you have a multiple signal path from a transmitter to a receiver. These multiple signal paths represent multiple waves. And as we know from elementary physics, when multiple waves interact, they could create constructive and destructive interference of the signal. Destructive constructive interference means that the channel will go from weak to strong as you move from a destructive valley to a constructive peak. Okay? So what is the time scale we're talking about here? So we are talking about essentially the time scale required to move a distance of the order of the carrier wavelength. Okay? So carrier wavelength for 900 megahertz cellular is about 0.3 meter. So that means as you move for a distance of 0.3 meter, you will see the signal strength changing significantly due to movement from peaks to valleys. Okay? So that's important to keep in mind. So we're talking about vehicular speed of the order of 100 hertz, variation. And now you can imagine you have a channel moving so fast, fluctuating. This is essentially a driver. So we have to pay some respect to this picture, because this is the channel that we have to deal with as wireless communication engineer. So one should pay some respect, admire it a little bit, and then we move on. So let's think about some numbers here. So this is the time scale. So example, this is roughly 3 seconds. So within like a few seconds, first, you will see a lot of variation. This is the real channel, by the way. Real channel measured by courtesy of my Qualcomm friends. Actually, the EVDO system. So first, observation, variations are very fast. Okay. Second, the dynamic range is very high for this example. Going from peaks to valleys, we're talking about 16 dB here. So typically 16, 20 dB, that kind of numbers are not surprising. Okay? So very wide dynamic range. And basically that's the problem. We have to communicate over this channel. Okay? So that sets the stage. Let me try to understand where these numbers, in some sense, how these numbers, dynamic range or time scale, how these things depend on the actual wireless communication system that you're going to design. To do that, we want to look deeper into the channel modeling issue. And here, I want to understand two things. I want to be able to convey two things to you in the next 1 hour. And the two things I want to convey is the following. One, whenever you are given a wireless system to design, you're typically given a bunch of basic physical parameters associated with this system. So for example, you may be given the carrier frequency, whether it's 900 megahertz or 1.9 or 2.4 gigahertz. You're given some kind of mobility speed. Are you designing for an indoor environment where people just walk around? Are you designing for an outdoor environment where people in cars? Are you designing for a fast train where you're moving at 200 kilometers per hour? So the mobility speed is a parameter that dictates the regime of operation of the system. Or you're also given the bandwidth typically. So in IS-95 CDMA, this is the CDMA city here. So we talk about CDMA. 1.9, the bandwidth is, people know, right? What's the bandwidth of a CDMA system? 1x, 1.25 megahertz, 1.25 megahertz. Oh, by the way, I will use a lot of numbers as I go through the course, because I think numbers really gives you some sense of the orders of magnitude that we're talking about here. So I'm not so much interested in 1.25 megahertz versus 1.10 megahertz. I'm really interested in some orders of magnitude. So I think it's good to keep some numbers in mind. Okay? So bandwidth, delay spread, that's also an important parameter. Delay spread is roughly what's the range of delay of these multipath. Angular spread, the range of angles of the multipath. These are sort of numbers that are, in some sense, a function of the environment that you want to operate at. Okay? So in an indoor environment, delay spread is smaller. In an outdoor environment, typically delay spread are longer because paths travel longer distances, longer delays. Okay? So you typically have a sense of all these few numbers. And now from a wireless communication engineer point of view, you want to be able to understand how these parameters affect the wireless channel. Okay? The wireless channel is an object, but from our point of view, we want to focus on how the wireless channel behaves from the communication system point of view. In other words, how my information bits, how my bits going to see the channel. Okay? So that's the first thing I want to convey. And then the second thing I want to convey is really how to model this wireless communication channel. So our strategy here is we start from some deterministic examples, and then we progress towards statistical models. So one, we understand the influence of those parameters on our model. Two, we want to develop a model so that we can use those models to do performance analysis and as a basis for designing new and cool ways of communication. So a model is very important for us. So that's the two things I want to accomplish in this first section out of 6 or 7 sections. I can't remember how many sections there are now. Okay. So physical model. So by physical model, I mean essentially a model which is a function of the physical environment, so a deterministic model. Okay? So wireless channel is a great thing for teaching undergraduates, actually. I really push very hard for teaching wireless modeling for undergraduates because it's really a prime good example of the power of linear system thinking. Because to a very good approximation, wireless channels are really linear. So here we have the received signal is the sum of a bunch of delay version of the transmitted signal attenuated by some gains. So remember our picture here, multipath. Okay? So here we have the example of 3 paths. For each of these paths, they are associated 2 numbers. 1, the delay. In other words, how long does that path take to get from the transmitter to a receiver? And 2, the gain or attenuation. How much attenuation that path has gone through. So those 2 numbers are captured in this model, okay, AI and tau I. The more general model that I'm considering here, these guys are a function of time t. Okay? So the delay and attenuation are both a function of time t. Why? Because as my environment changes, as I move around, the delay of the path, the length of the path changes, and therefore the delay changes. The attenuation changes as the path gets longer or shorter, etc. Okay? So these things are in general time varying. So this is a linear time varying system. System is linear. It's a superposition of a bunch of delay versions of the signal, but it's in general time varying. Okay. So once we have a linear time invariant system, then we can think of it in terms of an impulse response, which is, in this case, a bunch of delta. Okay? 1 delta associated with each path. All right? So to focus on to simplify the problem first, we will first consider the case of a linear time invariant channel, h tau equals sum of ai delta tau minus tau I. Okay? So as I move now to equations, from words to equations, please, whenever you have any question, please stop me. Because if you stop me, it's good because I get a sense also where you are. Otherwise, I go off in a completely open loop process, then who knows where I will be. Because I'm not teaching this to myself, right? So I have some understanding of this material. So I want to convey to you. So it's important for you to ask me questions for me to gauge where you guys are. Okay. Sum of AI delta tau minus tau I. So in the time invariant case, you can think of the mobile as the transmitter, receiver, and the environment, everything is static. So that these gains, AI, and the delay tau I are all fixed. Okay? So that's our simple model here. So the first thing that one does when one thinks about the wireless channel from the point of view of the communication system is that two things. One, the communication typically takes place at a very high carrier frequency. All right? Two, the processing typically happens at the baseband. So in a typical digital communication system, you do processing at the baseband, and then after you process that, you shift it to the passband and you send over the air. Okay? So we're mainly focused on baseband processing here. So that's why we need a conversion. And here's how it works. You want to stop me so early already? I only started for like 10 minutes here. Okay, so typically what you do is you start with two signals. Since most people have taken digital communication, this should be familiar. I and Q phase, okay? You modulate it by some sinusoid at the carrier frequency. You shift it to the passband. You send it over the channel, which has an impulse response h of tau. At the receiver, you do down conversion. You shift it back down to the baseband. You filter it to make sure that you have the signal within the bandwidth of interest, okay? And output, it goes, okay? So the fact that we're looking at the channel from a baseband point of view necessitates that we have to do complex numbers. So when I teach an undergraduate class at Berkeley, whenever I say the word complex numbers, the students look at me, whoa, complex. So I think it's a really bad terminology, right? We should have called it simple numbers. Why do we call it complex number? I don't see any reason whatsoever. In any case, but now we're forced to look at these complex numbers. And this picture shows you why that we have to look at complex numbers in the frequency domain. So what we're really doing is that we start with a baseband signal, and then we shift it to the passband. And the shift to the passband is really this operation of converting this baseband signal to the passband. So you can see that in the passband, you have conjugate symmetry. So it's a real signal, of course. We may want to think in terms of complex number, but we're dealing with the real world, and therefore we send real signals. So you have conjugate symmetry, but if you shift it to the baseband, you're just taking half of this thing and plug it here. So you can see that this thing has no conjugate symmetry, and therefore the signal is necessarily complex. And in terms of time domain, we're thinking of this as the real part and this as the imaginary part of that complex signal. Okay? Great. Thank you very much. Okay, so that's the picture. So now we got to ask ourselves, what does the channel look like in the baseband point of view? So you can look at this picture. What I do, I start with the baseband signal. I convert it to a passband signal. I send it over the air. So over the air means what? Okay. Now I got to ask the same question again, right? Can you see this word? It was already calibrated. Okay. All right. So this is the passband signal. This is going to go through a channel with a certain response. So this part will go through the channel at this particular frequency range. And if I shift this from a baseband point of view, the channel I see from the baseband point of view is therefore nothing but the baseband version of the channel, which is basically the channel shifted by the carrier frequency f. Okay? So that HB of f is the baseband representation of the actual physical channel. Okay? So this is the key operation. All I'm doing is I am shifting it by a carrier frequency fc of the original channel response h of f. H of b is now my baseband channel response. In the time domain, we know from signals and systems that if we shift in the frequency domain, that means we're multiplying by e minus j2 pi fct in the time domain. Okay? If we plug back into the formula that we had earlier, that is h of t is a bunch of delta, then all we're doing is we're changing the gain here by multiplying by ej2 pi fc evaluated at the various tau I. So now we get the baseband gain. Okay. So this is our baseband representation in the time domain of our actual channel. This is what the signal will see. And so the gain, the baseband gain, which I denote by AI superscript B here, is given by two components. One is the amplitude AI, and the other one is the phase rotation, for phase shift, proportional to Fc times tau I. So this is really just a complex phasor representation of a time domain signal. Okay? So that's the model that we're going to look at. The important thing to remember is that each path is associated with a delay and a complex gain. The delay is tau I, and the complex gain is given by AI times ej2 pi fc tau I. And notice that the delay enters both tau I, of course, and also the complex gain. Okay? So it's intuitively easy to think about this way. If you have a certain delay, that translates to, in terms of the baseband, a rotation of the complex number. Okay? All right? Okay. So this is the first step. The second step now is we have to convert it into discrete time. So physical channel is, of course, continuous time, but we are dealing with a digital communication system here, so we operate in discrete time. So in the discrete time, what does that mean? That means instead of sending a waveform, I'm now sending a sequence of symbols. These are typically coded symbols. Okay? I modulate it by a waveform so that I have basically a train of these symbols modulated by this shifted version of these waveforms, and then send over the air. Same thing for the imaginary part as well. Okay? This waveform can be many different types of waveforms, but for simplicity, we focus on the most simple waveform, the sync waveform. So we have a bandwidth of interest W, okay? And these waveforms, we're essentially operating at Nyquist rate here. The waveform is consistent with the bandwidth W. At the receiver, I basically filter it to the bandwidth of W, and then I sample at the receiver, sampling. Sampling means projecting it onto the sync function. So that operation matches the transmitter. Now, if you use a different waveform, typically in wireless communication system, people don't like to use sync waveform. Sync waveform is really the type of waveforms that theoreticians like because it keeps everything simple. But in reality, of course, you want to use some kind of raised cosine pulses and so forth. Then you do a slightly different thing here, but it doesn't really affect qualitatively what we're going to talk about. So we're going to just focus on sync waveforms here. So now I'm showing my theoretical roots here. Okay. All right. So now what do we have here? Okay, so the sampling. So what are we doing here? So now again, we go back to the channel. What does this sampling and modulation process do to the channel itself? And so now we have a discrete time channel. Okay, so the original continuous time channel is sampled because now my input symbols is discrete time, my output symbol is discrete time. So the original linear time invariant continuous time channel becomes a linear time invariant discrete time channel, where HL is a complex number reflecting the gain of the channel, the gain of the baseband channel, after a delay of L symbol time. Okay? So here we introduce notation. Notations cannot be avoided. Engineers have to deal with notation. So let me introduce it right off the bat to make sure that, and I hope that my notations are consistent, which is, so here's a different notation we use. M, we always use to denote the symbol index, the mth symbol. Okay? Script L, we always use to almost always, it's always an exception, to denote the delay in terms of number of symbols. So this says what? This says that the received symbol at time m is a sum of the previous symbol transmitted multiplied by a certain delay depending on certain gain depending on the delay, h sub l. Okay? So this is my discrete time channel. And this is the channel that I'm going to see. So the fact that you have multipath, is reflected in the fact that the system has memory. That is, the previous symbol may affect what you see currently because those paths take some time to get here. Okay? So now, since we need to understand how the wireless channel behaves from given physical parameters, so we need to be able to connect what this discrete time channel is, or in other words, what these taps are, in terms of the physical multipath. Okay? So now I start using a whiteboard. If you don't mind, I'll shift the whiteboard back here. Is it okay? Because this has a light here, so it's probably more visible. Okay. Okay. Now, so what's happening here? If I look at the delay in continuous time, okay, and I plot, let's say, the locations of the paths, let's say the first path arrives at time tau 1, the second path arrives at tau 2, the third path arrives at tau 3, etc. And then I plot the gains of these paths. Typically, the ones arrive later are smaller because they have gone through a bunch of reflections already, and so forth. Okay, maybe there's another path here at tau 4. Maybe I should have this in order. Okay, so now, these are my paths delay. Okay, so this is a continuous time picture. Continuous time picture. Now, we want to relate this continuous time picture to our discrete time picture because discrete time is what the communication system sees. Continuous time is the physical reality. So to be able to connect physical parameters to the discrete time, to what we see, we need to be able to understand how we move from the continuous time channel to the discrete time channel. Okay? So now, how do I see this? What was the connection between the h sub l with these paths? Anyone can tell me? All right, audience participation. So people look at my slides, of course. You have copies of my slides already. I told you not to distribute them beforehand. Okay, so, well, the easiest way to think about this is the following. Okay? I have a certain bandwidth, so I'm transmitting symbols every, how many seconds? 1 over W. Remember, if you remember your digital communication course, maybe you got confused. I said, shit, 1 over 2W, 1 over W. There's always this mysterious factor of 2 lurking around. There's no factor of 2 here because I deal with complex numbers. Okay, and that's a bunch of complex numbers. You don't deal with factor of 2. So 1 over W is your sampling rate. Okay? So therefore, if I look at all these paths, okay, if I look at all these paths, I could, basically what I'm going to do is the channel will be sampled. So in other words, I now have a, is there a different color? No different color, only one color. Okay, that's fine. So let's say this is a 1 over W. Let's say this is 2 over W. Okay? Now, the channel bandwidth is limited means what? Means that essentially all the paths that arrive at time between 0 and 1 over W is essentially lumped into one number, which is my tap gain H sub 1. And then another bunch of paths is lumped into another number, which is the second delay. Okay? So the fact that I have a bandwidth limitation means that there's a limitation on how much I can resolve these multipaths in the delay dimension. Okay? Bandwidth limitation means what? Means that you're given a bandwidth limitation, and therefore paths that arrive at a slightly different time, much less than 1 over W, cannot be resolved. You can't really figure it out because you have limitation on your bandwidth. Bandwidth limitation means delay resolution limitation. And so the one way to think about it is you have a continuous time channel, and once you sample it, what you do is essentially you throw a bunch of these paths together, and you add it up. So AIE minus J2 pi FC is exactly the complex gain here. And they get added up together to form one tap. So in this notation, I call this HL the Lth complex channel tap. So what is this sum over? This sum is precisely over all the paths that fall in the delay bin, which is L over W minus 1 over 2W and L over W plus 1 over 2W, the Lth bin. So in this picture, what I'm doing is I am essentially breaking up my delay dimension, continuous, into bins of size 1 over W. Okay? And all the paths that arrive in the same bin, from my point of view, I can't really resolve them, so I group it into one number. Okay? All right? So of course, this is an approximation. This is an approximation. In practice, there will be some spillover, but I sort of ignore that. To a first order, this is the right way of thinking about it. So paths that arrive in the same delay bin will contribute to the same tab. Okay? Is this picture clear? So this is rather basic, a lot of people may think, but this will become useful when we talk about MIMO tomorrow. Okay? Because in a MIMO, which is a more complicated problem, I will essentially apply the same strategy to think about MIMO communication. Okay, any question? All right. So, and that's a very important point, is that if your bandwidth is W, the resolution of multipath will be up to delay of size 1 over W. Okay, then we're ready to think about fading. Okay? So now we can think about how fading occurs. So what does fading means? Fading means that essentially the gain may become very small or may become very high because of constructive and destructive interference, right? That was the physical explanation. In terms of this mathematical model, we can also see fading, of course, because this is the channel that our communication system will see. Okay? Now, why do we see fading? You can see it in this picture. In the continuous time case, I can see exactly all these individual multipaths, right? And so therefore, there's no fading in continuous time. Fading is an effect which is dependent on the fact that you have a delay limit, you have a limit in delay resolution because you have a bandwidth constraint. Why? Because if I have no bandwidth constraint, I can always see these individual paths. They never cancel each other. Remember, fading is coming from destructive interference of signal. If I see them, each one individually, there's no fading. I have access to the signals coming from individual paths. I can do whatever processing. The fact that we have fading is because we have a limit in bandwidth. And therefore, we cannot resolve some of these paths. This one maybe we can resolve, so it's good. But then these guys, we cannot resolve. And what happens is that if they happen to be out of phase, pi 180 degrees out of phase, then each of them may be strong signal, but they cancel each other. And what we see is a deep valley. Okay? So that's a very important point that I want to mention, is that fading, which is the issue that a wireless communication engineer is most afraid of, is because of the bandwidth limitation. Because of bandwidth limitation. You cannot resolve paths, and therefore paths can cancel each other. Okay? So canceling each other is essentially the same way of saying that you have destructive interference between two waves that arrive at pi out of phase. Okay? All right. So that's the number one point. Fading occurs when destructive interference of multipath. And now we want to think about two types of channel. Okay? One is called a flat fading channel, and the other one is called a frequency selective fading channel. Okay? What does a flat fading channel mean? Flat means that the frequency response is flat. Frequency response is flat is equivalent to saying that the impulse response is what? All right, I got to get people thinking now. Sorry? A delta, right? The discrete time filter should be a delta. A delta means one tab, essentially. So in other words, when we all have essentially one tab. So all this is approximation, of course. You never have a single tab channel. You always have some spillover into later tabs. But let's just, as an approximation, when will I have a single tab? I will have a single tab if all these paths are unresolvable and they all get thrown into one delay bin. The delay bin is of size 1 over W. So therefore, when the delay spread of these paths, that is, the range of delays, is less than 1 over W, then approximately I have a flat fading channel. Okay? So that's why the delay spread is an important parameter. Okay? So the delay spread is the range of the delay, and if this number, if the delay spread is much less than 1 over W, what is W again? W is the bandwidth, so 1 over W is my symbol time. Then all these paths essentially arrive, from my point of view, into one tab. And therefore I have a flat fading channel. So the channel, if you look at the frequency response, is flat. In the time domain, it's like one tab. Okay. Now, you can rewrite this condition, TD much less than 1 over W, by a different condition. If I take the reciprocal of TD, then I define this number to be what I call coherence bandwidth. So in this section, there's a whole slur of terminology coming up. You just cannot avoid it. You know, terminology is terminology. You got to talk to people, and you got to understand the terminology. So the coherence bandwidth is the reciprocal of TD, and so this condition can be rewritten as the coherence bandwidth is much greater than W. So that's why we call it coherence bandwidth, because this is the bandwidth across which the channel remains more or less constant. Is reciprocal to 1 over TD. And if this is much larger than W, then we have a flat fading channel, because in the bandwidth of interest, the channel is flat. Okay? Otherwise, if the bandwidth 1 over W is less than the delay spread, then you start seeing this phenomenon. That is, you start seeing paths group into different tabs, and therefore you have multiple tabs, and therefore your channel is frequency selective. So that's the other types of channel with multiple tabs is frequency selective. Okay? So that's our basic characterization, is in terms of the delay spread. Okay? So delay spread is the key parameter. Okay? So one thing I want to emphasize is that the channel, the continuous time channel is what it is. The discrete time channel is the channel that we see in a communication system. Depends not only on the physical environment in terms of delay spread, but it also depends on my communication system, which is the bandwidth I'm operating at. So combining the physical environment in terms of delay spread and the bandwidth together, I can tell whether my channel is frequency selective or flat fading. Okay? So this is an example. This is a channel with a particular bandwidth of 200 megahertz. So I have a given physical channel here. I look over 200 megahertz, so I'm sampling at of the order of nanosecond, and I see this channel. And I see a lot of ups and downs. If I now narrow my bandwidth to, let's say, 40 megahertz, then I see less variation of the channel. So the channel becomes flatter. And in a discrete time, there's less resolution, and I see fewer taps. Okay? So that's the important thing to emphasize, is that how the channel looks like depends both on the environment and the bandwidth. Okay? So we'll continue this theme as we talk about MIMO tomorrow. Okay, but bear this in mind. All right, so far, I have talked about a linear time invariant channel, and I'm focusing on the frequency domain attributes. In other words, how the frequency domain of the channel, how the frequency response of the channel depends on the physical environment. Okay? The second thing I want to talk about is time variation. So now I'm going to bring time variation into the picture. All right? So here is an example. I have my Ferrari here. Alon promised me that if I teach here, this will be my reward at the end of the day. Yes? That's Padavani's Ferrari. But Padavani is not teaching here. Maybe that's why I'm teaching. No, he's not teaching. Okay. So you have this car example. We have this transmit antenna. So this is my base station, maybe. There's a wall here, and this Ferrari is going towards the wall here. It's not stopping. It's at 60 kilometers per hour, constant speed, constant speed. Now, I'm moving, and therefore, what happens is that the channel will vary. Okay? Now, let's think about it from a physical point of view. Why is the channel varying? First of all, the most important phenomenon is that you should recognize is that suppose I'm operating at a carrier frequency of 900 megahertz, cellular bandwidth, cellular carrier frequency. Suppose I send a sinusoid at that frequency. Okay? Can anyone tell me whether if I receive a signal here, will it still be at 900 megahertz? Got to start thinking about wireless now. And now you're going to remember your high school, primary school physics. What will I receive? Will I receive a signal at carrier frequency 900 megahertz, larger than 900 megahertz, or smaller than 900 megahertz? Who thinks it's 900 megahertz? Who thinks it's more than 900 megahertz? Who thinks it's less than 900 megahertz? Right. It's less than 900 megahertz because of an effect called Doppler. You have a waveform coming in. You're moving away from it, so the wavelength gets stretched by a little bit, and therefore the frequency gets reduced. And the Doppler shift is reduced by, in this example, 50 hertz. So 50 is equal to, so the Doppler shift, actually there's a formula for this, so I can write it down. Actually, I should ask, what's the formula? I don't remember these things anymore. I wrote my book and I forgot everything. Everything's in the book. Sorry? Oh, good. Then I can check it in case I forget. Okay, good. Alon takes good care of me. What's the formula for the Doppler shift? Let's think about it. What does it depend on first? It depends on the speed, v. Good. It depends on what? The wavelength. So this is the Doppler shift formula, where c is the speed of light. Okay? So this is the Doppler shift. I guess it should be minus sign here. Okay. So Doppler shift is proportional to the velocity of the speed of the object. and proportional also to the carrier frequency. Okay? So now we already immediately observe that we're dealing with a linear. Are we still working with a linear time invariant channel? How can we have a linear time invariant channel if the output signal has a different frequency as the input signal? Right? I'm sending a sinusoid at 900 megahertz. I get a signal of signal 900 megahertz minus 50 hertz. So I don't have a linear time invariant channel more. I have a linear time varying channel. Okay. Now, the more interesting thing is the reflected path. There's one reflected off the wall. And this path has a Doppler shift of what? Sorry? Plus 50 hertz. Okay? So the reflected path has a Doppler plus 50 hertz. You have a wave compression here going towards the wall. Okay? So now, the Doppler spread. So there's a terminology here, another terminology called the, by the way, there will be a quiz at the end of this section whether anyone can answer all these terminology questions. Doppler spread is 100 megahertz. Not 100 megahertz, 100 hertz. 100 megahertz would be a very fast car. Okay. So let's look at this in general, what's happening here. How does this Doppler shift enter into our model? So we have our model here. Ym equals sum of HL times Xm of L. The only thing that changes when we introduce time variation is now that this index, this tap gain, is a function of M. All right. Now, quick review. Notation. L dictates what? Sorry? Everything is symbol index, though. L and M are all symbol index, but what do they physically represent? No. No, it's not number of path. A tab. It's a tab index. L is a unit of delay. Okay? So delay and time, of course, have the same units, seconds, or symbol. But it's important to distinguish. So L is the delay because it represents the gain at a delay L symbol. M is just a symbol time. It's not a delay. Okay, that's how you distinguish between L and M. So I put M here because now H of L is now time varying. So the tabs are now changing with time as you move around. Okay? So I just wrote down the same expression as before. H of L is the sum of the baseband representation of the channel gain. But now I put back the time variation into the amplitude and the delay, tau ft. So now we have the general expression here. And now we can investigate what happens when time changes. Okay? So first of all, the Doppler shift, if you look at this expression, in that example, the Doppler shift is essentially proportional to the carrier frequency, as we have it there, times the rate of change of the delay of the ith path. So in that example, that happens to be exactly V over C. Okay, so the Doppler shift corresponds to exactly the rate of change of this phase. As you move around, this thing is changing at a certain rate. And that rate is precisely Doppler shift. All right? If you want to forget about Doppler shift, that's fine. But you can see that this term, the variation of this term, will be a cause of the variation of the gains here. Okay? So the picture is, as my car moves away from the transmit antenna, the frequency shifted, but that also means that the phase is changing linearly. Okay? The phase is changing linearly. So the way to think about it is the following, that each of these guys are rotating. Okay? So tell me, Suppose all the paths are rotating at the same speed. Okay? All right? Will I see any variation of the channel? So now I want to connect the physical environment again to what my channel will see. Will the channel vary? So suppose all these guys are rotating. So what am I doing here? Okay? So I am adding, let's say I have two paths here. I have one path with a baseband complex channel, this. Okay? Another path maybe here. Okay? All right? So now, as time changes, the phase changes. So this thing rotates. Okay? And suppose this thing rotates at the same speed as well. Okay? So what will happen to my channel? My channel is the sum of these two guys, will also rotate at exactly the same speed. Okay? So the phases of the channel gain changes. However, do I see any fluctuation in the magnitude of the channel? Which is the most important thing for me, because I want to know whether the channel is going up and down, right? So the channel does not really go up and down, because these guys are just the same rotation speed, so the whole thing will just rotate. If it's strong to start with, then it will remain strong. If it's weak to start with, it will remain weak. So the reason why we have channel variation, okay? The reason why we have channel variation is because these two guys are rotating at different speed. In other words, different paths, if they have different Doppler shifts, then what happens is that this one, suppose this one rotates faster than this one, then when this one becomes aligned with this guy, what do we have? We have a peak. When this guy becomes 180 degrees off from this guy, there'll be cancellation, channel becomes weak. So as you move around, the channel will become strong and weak, depending on whether you have constructive, destructive interference. And so you have variation. And the variation is coming from Doppler spread. So the important thing about how fast the variation is not the absolute Doppler shifts, but the spread of the Doppler shifts. Okay? So the spread of the Doppler shifts is essentially the range of the fastest and the highest and the lowest Doppler shifts. If my Doppler spread is very high, then that means this one is moving very fast relative to this guy, and therefore the peaks and valley will come in a hurry. If the Doppler spread is very small, in the extreme case when there's the same rotation speed, the channel never varies. So if the Doppler spread is very small, then the variation will be very slow. So the important thing is the Doppler spread. Okay? So you can also think from this picture is that these two paths are, because they're coming from different directions, okay? Coming from different directions, they are essentially creating constructive and destructive nodes. And as this column moves, you're going up and down. So that's another way of looking at it. Okay? All right. So that's why we define the coherence time to be the reciprocal of the delay spread. That is, the larger delay spread, sorry, I screwed up. I'm losing it. What is this? Doppler spread. So this is very easily confused because it's like DS, you know. This is just to confuse people, prevent people from entering the field. Too many people in the field already. So you introduce all kinds of terminology and to make people frustrated, like people like discrete people like Alon is like, oh man, this is too much stuff. I don't want to deal with it. Okay. Coherence time is the reciprocal of the delay of the Doppler spread. Okay. So, okay, let's talk about Doppler spread. Let's talk about Doppler spread. Okay, so what do we have? When we talk about whether the channel is flat or frequency selective, okay, that depends on the delay spread. And the delay spread is very naturally connected to the physical environment. That tells you the range of delays of the path. We want to do the same thing here. So now we want to connect the Doppler spread to physical parameters. Okay? So let's look at our expression again. The Doppler spread is the range of the delay, the rate of change of delay. So first observation is that the Doppler spread and the delay spread, are they related? Are they related? No, they're not related. They're nothing to do with each other. Because the delay spread is the range of the delays themselves. Okay? The Doppler spread is the range of the rate of change of the delay. So one is the derivative, and the other one is the quantity itself. So they have nothing to do with each other. You can have a very large delay spread and a very small Doppler spread, and vice versa. It's not necessarily correlated. So that's the first thing to make sure that all these quantities are defined in terms of the delays of the paths, but they are very different quantities. One is the delays themselves, and the other one is the derivative. Okay, that's number one. So now if we look at this formula, then we can ask ourselves, what does the Doppler spread depend on? Well, the Doppler spread will be proportional to, obviously, the carrier frequency. Okay? The larger the carrier frequency, the faster the shifts. Okay? And therefore larger the spread. So therefore, if you are designing a system for 900 megahertz versus a system for 5.3 gigahertz, you would expect much faster variation at a 5.3 gigahertz system. Okay, that's number one. That's an important thing. Number two, which is more subtle, is that it depends on the angular spread of the arriving path. Okay? Now, why is that? So let's understand what's going on here. That's a point that is important when we think about MIMO. Okay. So let's say okay. So I'm moving at a certain speed, v. All right? Okay? The path is coming, suppose I have a path coming in this direction. Okay? So the Doppler shift is proportional to v, of course, proportional to carrier frequency, but it's also a function of another thing, which is this angle, theta. Okay? And why is that? Because remember, the Doppler shift is proportional to the derivative of the change of the delay. Okay? Now, if I'm moving at a certain speed, it's not only a function of speed, but also which direction we're moving. Okay? For example, I claim that if I move in this direction, if I were moving in this direction, then my Doppler shift associated with this path is essentially 0. Because I'm moving perpendicular to that. So locally, there's no change in the length of this path as I move. If I move in the direction of the path, I maximize the Doppler shift. So it's a function of the angle. In fact, it's proportional to cosine of theta. Okay? So therefore, not only the Doppler spread, a function of the speed of the vehicle, which is natural. The faster you move, the higher the Doppler spread. But it's also a function of, individually, the Doppler shift is a function of cosine of the angle. Okay? So it's VC times cosine theta I. And therefore, the spread is a function of how much spread you have in the angles of the path. If you have paths that are bunched up together, am I doing something to this? Fast fading. But we haven't figured out, we haven't gone to how to design a communication system yet, so we're not getting information through at this point. Okay? So if the paths are coming from very similar angles, okay, then the Doppler shift, then the Doppler spread is very small. Why is this important? Because depending on what kind of environment you have, you may have very limited Doppler spread, very limited angular spread. Imagine I have a base station, a tower. You're looking at very far away, and there's very little local scattering around you. Then the angular spread is very small. If you're on the ground and there's a lot of stuff around you, like my office, a lot of clutter, then there's a lot of angular spread. So in different scenarios, you have very different angular spread. And what this tells you is that that one connection of angular spread is with the Doppler spread. The bigger angular spread is the bigger Doppler spread. Okay? So that's an example of the connection between the physical parameter and the channel. Okay. All right. At this point, we take a break. Yeah?
Is there any evidence that Doppler spread is worse when you're in oncoming traffic, two-way traffic, because your walls are moving?
The walls are moving?
Well, you have vehicles passing by each other.
Yeah.
Experimental evidence for that?
Oh, you mean like in a two-way street or something? Yeah, I don't know if there's any experimental evidence, but it seems to make sense. So if your scattering is coming from your vehicles around you, then you would expect so. You would expect so. Because on a one-way highway, your speed is the range of speed is very small, right? Relative speed between you and the other vehicles. So that seems to make sense. Don't know if there's any experimental study. Okay, let's take a 10-minute break and we'll resume.